Okay, I think we're all set. Thank you for having me back. I've been a member of Solvera for a year. I was invited into the group by Claudio, who I know from teaching at the Cole program in Keene State College, part of the continuing ed program. And I spoke, as Pat said, just a year ago, so I was delighted to be invited back. I actually taught a course in the Introduction to Cosmology in the fall term at the Cole program. And so when I was invited a few weeks ago to give a talk, I thought that would be a natural thing to think about what I was doing in that course. And what I'm going to talk about, the Hubble constant controversy, is something I actually touched on very briefly at the very end of the talk. Sorry, at the very end of my course. And so this gave me the opportunity, the invitation to speak here gave me the opportunity to go back and look at all of that and do a little bit more research and a bit more reading. And I think, give it a bit more justice tonight than I was able to do in the course. So let me get, okay. So we do have a situation in which the Hubble constant is being measured in at least two different ways, two different prominent ways. And not only do they not agree, but even their error bars don't overlap. And given the importance of the Hubble constant, this has been called by many a crisis in cosmology. And that's what I'll be talking about tonight. An overview of what I'd like to do is, first of all, what is the Hubble constant? Obviously, most of you here know that, but being the teacher in me, just to be self-contained, what is the Hubble constant? Why is it important? What is this measurement discrepancy? How are the actual measurements taken to understand this discrepancy? And what can such a large discrepancy mean about the underlying science? And finally, what can and is being done to try to resolve the problem? Okay, so let's start with what is the Hubble constant. We'll begin here with the notion of a redshift, a moving object making a wave phenomenon, sound or light, to an observer will have its wavelength or frequency distorted by its own motion. What we're interested in here is a source moving away from us, in which the wavelengths get elongated as they reach us. We call that a redshift. So if you look at a absorption spectrum, for example, here at rest, and you could see the shifting of a source that was moving away. Here, this double bar moves to the red, to the red, to the red. So this is the kind of shift that we're talking about in spectra, which gives us the information that this source that we're looking at is in fact moving away from us. And in fact, just setting up a bit of vocabulary, talking about lambda 0 being the wavelength of the light that we would see at rest, compared to lambda m, the measured wavelength of the moving object. C being the speed of light, given the wave phenomena that we're interested in, then we actually have a formula that can be derived for the velocity of the source of that wave. It's the speed of the wave times the ratio of the change in the wavelength, the measured wavelength minus the so-called lab wavelength, the wavelength measured at rest, divided by that rest wavelength. Lambda m minus lambda 0 is called delta lambda, and so the formula that we have is that speed of light, c, times that ratio, the change in lambda over lambda 0. That change in lambda over lambda 0, traditionally the letter is given as z, and that is the redshift. That's what we're talking about. So, for example, if you were to look at let's say this violet light here, say being very simple at the extreme here at 400 nanometers, and if it were shifted up into this region here, the yellow-green, up to 600 nanometers, then we would have a shift of 200 nanometers. Well, 200 over the 400 would give us a redshift of a half. If this violet light was shifted all the way up into the infrared, up to 800 nanometers, we would have a 400 nanometer shift of a 400 nanometer wavelength, and we would have a full Z of 1, a redshift of 1. If you look at the formula, that seems a little strange because that would give us something moving at the speed of light, and that could be a problem. We'll address that when we get to it. But as long as Z stays modest, say certainly up to a half or so, there's really no problem using a formula like this, and even a little beyond. But as we get to higher redshifts, which we will, I'll talk about how that can be accommodated. So this is the basic notion that was first studied by Vesto Slipher in the early part of the 1900s. And he was the one who began taking spectra of distant, what he called, what we all called at that time, nebula. And he noticed these redshifts, that most of the nebula exhibited redshifts. Some blue, but most red. And the story goes that it was George Lemaitre in 1927 who first noted this trend that as you look at the shift, as you look at galaxies, nebula, further and further away, the redshift gets greater and greater and greater. And so clearly the conclusion is that as we see objects move further and further away, they're moving away from us faster and faster. And so Lemaitre then has the idea of the expanding universe, the beginning of the idea of the Big Bang. That was brought formally with full research, of course, by Hubble in the famous graph of his data of showing distance with speed and having the linear relationship, and that the further the nebula were away from us, the faster they were going. And in fact, it was a simple linear relationship. Making a linear relationship into a formula, of course, requires a constant, so the velocity is proportional to the distance. The constant of proportionality has become Hubble's constant, universally written as h sub 0. The 0 meaning this is the current value of Hubble's constant. It doesn't mean that this expansion rate has been the same for the whole time of the universe, but this is the rate that we have right now in anything from the near past. This is what our focus will be tonight, the measuring of this number, h sub 0. That rate of recession as distance grows. And here again, just to make the point of the redshift, here we have the H and K bars here of a spectrum. See that vaguely there's 2 bars right here. And as we get to objects which are moving further away, faster and faster, the shift is getting greater and greater and greater. Okay. Here's a more modern graph with lots of data coming today, and we now have h sub 0 pretty much solidifying basically around the number 70. The units, 70 kilometers per second per megaparsec. Okay? So for every megaparsec, a megaparsec, a million parsecs, 1 parsec is 3¼ light years, so a million parsecs, 3¼ million light years. So for every million parsec that we move out, these objects will be moving 70 kilometers per second faster than the group before. So it's measuring the rate of increase of speed as we increase our distance. So in its simplest form, Hubble's constant is truly velocity over distance. Velocity, kilometers per second per distance. And this is the traditional units that are used for Hubble's constant, kilometers per second per megaparsec. What this phenomenon leads to and what is concluded from it, can be concluded by it, is the universal expansion of space. So we have here, for example, some spots. We are here, let's say, looking at 2 distant objects. And if the universe is expanding consistently, constantly over time, then if this distance here has grown from 1, for example, to 3, then this distance here will have grown, let's say, from 2 to 6. So if the expansion is uniform, it will in fact lead to Hubble's law. And so Hubble's law is one of the germs of the idea of the expanding universe and the Big Bang. As we look at various graphs through the evening of Hubble's law, measuring Hubble's constant, I've given you here the simplest one conceptually of velocity versus distance, because in fact that's the way the law is stated, velocity versus distance. But in fact you won't see this very often. What you'll see more often is redshift versus distance, or even actually more common, distance versus redshift. The reason is because it's in fact distance and redshift that are the things that are being measured more directly. The velocity is only coming from the redshift. It's the redshift that actually is what's being measured. And so since redshift and velocity have, at least for low redshifts, a simple linear relationship, it's just as easy to plot against redshift directly. And accommodations will be made as z gets larger and larger as we move further and further out in distance. And we'll come to that when we need it. Okay, so first question down. Second question, why is the Hubble constant important? Well, our current understanding of the Big Bang model and all of its evolution of the universe from there, called the Lambda-CDM model, which I'll be talking about a bit later on, has a predicted value for the Hubble constant. Therefore, that value, that measured value, is a key parameter that tests the validity of that model. That actually is the core of my talk tonight. That in fact, since there is a discrepancy, is the validity of this model to be questioned. The current expansion of the universe as measured by the Hubble constant compared to the discovered slower expansion of 1998, which we'll come to, in the past necessitates the reintroduction of the cosmological constant into general theory of relativity, and therefore the creation of the new concept of dark energy. So this is all because of the Hubble constant measured now, in fact, does not square with what the expansion was long ago in the distant past of the universe. General relativity gives an important relationship between various parameters of cosmology. One is the Hubble constant finds its way into one of the beautiful Friedmann equations that's so elegant of the energy density of the universe, the current energy density here, epsilon. It's a wonderful set of constants, pi, gravitational constant, and the speed of light squared. I am not an expert. I have not followed the detail of all the derivations of these wonderful formulas, but they are among the prettiest in physics. So Hubble's constant plays in a very important relationship in the guts of that theory, which is embedded in turn in general relativity. And lastly, to mention the estimation of the age of the universe. Take a look at Hubble's constant, its speed over distance, distance over time, over distance. You clear that away and you'll get 1 over time. So 1 over h0 is in fact has units of time. Question is, what time would that be? Well, a simple little piece of algebra. If t is the age of the universe, then if we're given any galaxy, which is a distance d away from us, okay, going back to the beginning, if everything did start in the Big Bang, then as a first approximation, that distance should be its velocity times time, its average velocity times the time it's been moving, the length of time of the age of the universe. So solving for the age of the universe, it's equal to distance over the speed. But we can write this distance as Hubble's constant times the distance, which gives us 1 over h sub 0. So in fact, 1 over h sub 0 is a first approximation, and it turns out when you do this much more carefully using the relationships of general relativity, that this relationship 1 over h0 is a very good estimate for the age of the universe. And so taking that kind of average number that all the different measurements are buzzing around of 70, you can go ahead and do that calculation and get the number that we're all familiar with, the age of the universe as 13.8 billion years. So certainly the Hubble constant is right in the middle of the science of cosmology. It is incredibly important. Okay, what is the controversy? It's right here. Okay? Here we have two different ways, two different methodologies of measuring this number. One is focused on analyzing the cosmic microwave background. And that's thought of as moving forward from the Big Bang. So you're moving forward in time, taking the furthest light that we can analyze and moving forward to coming to concluding what is Hubble's constant now. The other way, going backwards, is to kind of, in a sense, measure things more directly, in a sense of looking at the actual law, Hubble's law, and measuring redshift and distance. Measuring those directly, going now backwards from things which are in our own galaxy to other galaxies, to going further back to redshifts, maybe to 1 to 2, and just doing lots of calculations, getting an average of what we find the Hubble constant being, taking redshift divided by distance. And we come up with a number in that way. And there are many, many ways in which this part is done, and we'll talk about some of them tonight. You can see the problem. The problem is that the error bars don't even overlap now at this point, and they haven't for some time, for about 10 years. According to the teams that work from the cosmic microwave background, their measurements, as far as they're concerned, are accurate to 1%, given the theory that they're working inside of. For the what called here the CDL, the cosmic distance ladder people working backwards, their error bars are within 2%. They're also pretty confident of their number. So we have the very interesting situation that the advocates of each group are convinced that the other group is wrong. So certainly defines to be the technical term, right, of a tension about the measurement of the Hubble constant. So here's our current situation. I'm going to talk about kind of two different ways of using the CMB to measure Hubble's constant, and then a number of different ways here of measuring Hubble constant using the straight distance and redshift relationship to come up with. And you can see the problem. We have a cluster here with the CMB. We have a pretty good cluster here for looking at redshift and distance. And right in the middle, with very, very long error bars, to be sure, is one other way, which also is a redshift and distance measure. This one seems to be the only one that's touching both. And some people would love to say, well, okay, we're all done. We'll take this measurement here, our problem solved. But neither one of these two groups is about to agree to that. So what we'll do is we'll get started. Again, the one group is the moving forward kind of methodology. The other one, the moving back from current back to reasonable distances to measure that current Hubble constant. Okay, so let me stop here. And Eric, ask if there are any questions so far before I go into the first kind of measurement using the CMB.
Certainly, we do have a couple of questions here. Let me just scroll up in the chat. All right, Margot asks from a couple slides back, the H and K, are those the hydrogen and potassium emission lines?
Yes, that's exactly what they are, yes.
And Rick asks, might it be productive to ask, what might it mean if both groups were right?
That definitely is a philosophical question. What is truth? So I'm going to leave that to Eric.
I would go further and say, I think if both groups are right, there's some fun physics we're hopefully about to figure out over the next generation. So that's the only two questions in chat. I just want to say this is a time that if you'd like to unmute yourself and ask your question verbally, that is the place to go. Oh, and Rick just followed up saying, that's what I'm suggesting. I'm not sure. Rick, do you mean what is truth, or do you mean new physics?
New physics. I mean, rather than put our energy into saying, no, no, I'm right, you're wrong, just stop for a second, take a deep breath and say, well, if they were both right, what then? What explains that? I don't know, that just might be productive.
Rick, you're preempting my last slide.
Oh,
Thank
sorry.
you.
I'll
It's
mute
okay.
myself.
But I think you've thrown us off by using the word right. There can't be both right. What you mean is, in fact, within their theories, that data is correct. That conclusion is correct given those theories, not the fact that they're both right in the global philosophical sense. And yes, you definitely have preempted my last slide. So.
Rick apologizes. Does anybody else have any questions that they'd like to unmute and go for?
It's just the mark of a good presenter when somebody can ask a question like that.
Okay, should I continue? Eric, should I continue?
I'm not seeing anything else, so go for it.
Okay, so we have two paths to go down. Let's talk a little bit about the Lambda-Cold dark model. That's where that Lambda CDM acronym comes from. Lambda, of course, is the symbol used for the cosmological constant, and the cold dark matter is another fundamental piece of the model, of the theory that explains the Big Bang and all of its subsequent development, and so the name, the Lambda-Cold dark model. What we're concerned about is right here. We're concerned about the releasing of the CMB upon recombination. So let me take 3 slides. And again, I ask for your indulgence, because if we are going to question this model, I think it's worth looking at it for just a moment and see if we're going to overturn this thing, just what are we about to overturn or thinking of overturning. So again, I'm going through material which I realize is very, very familiar to most of you, but indulge me on this. So the model accounts for some of the fundamental properties of the universe: the expansion of the universe, the cosmological principle, that on the larger scale, the universe is homogeneous and isotropic. On the larger scale, the geometry of the universe is flat. That is, it obeys the Euclidean postulates of 3-dimensional geometry. The observed abundance of primordial hydrogen, deuterium, and helium. Okay, what we observe actually is explained very, very beautifully in this model. The existence and structure of the cosmic microwave background itself, its existence, its prediction, and so much, as we know, the structure of it has been actually built around building this model. The large-scale structure of the distribution of galaxies, and finally, the changing rate of expansion of the universe. Yeah, the changing rate that we all had to live with, given the great discovery of 1998 and the introduction of lambda, the dark energy. Okay, what are the fundamental assumptions? Not surprisingly, the fundamental assumptions of this theory, of this model, are the 2 pillars of modern physics: general relativity and quantum particle physics. So it is assumed that the general theory of relativity is the correct theory of gravity. It is assumed that dark energy is a manifestation of the non-zero cosmological constant in the equations of general relativity. You may not agree with these things, but if you're going to understand the model and make deductions from the model, these are the assumptions that you have to give the model builders. Quantum theory and the standard model of elementary particles is the correct theory of matter, energy, and forces on the smallest scales of the universe. And finally, dark matter is a yet undiscovered particle which creates a gravitational field, right? Interacts gravitationally with itself and the rest of matter, and which upon discovery will find its place in the standard model. That's an assumption and a hope and a prayer, I imagine, which seems to be becoming dimmer and dimmer as I read the literature among the particle physicists. But upon its discovery, which has not yet been discovered, they do hope it'll find its way into the standard model. So these are the assumptions, and like I say, the assumptions are the fundamentals of modern physics. This is not weird stuff. And finally, what is the fundamental evidence that this thing rests on? Well, Hubble's law, the first one, okay? That the universe is expanding according to this, this centrally linear relationship with redshift. The calculation of that observed abundance of the primordial hydrogen and deuterium and helium, you can actually calculate this from the model. The prediction of the CMB itself, the calculation of its black body spectrum, which we find to be exactly that. We know that the black body spectrum of the CMB is the best example of a pure theoretical black body spectrum we have in the universe. We cannot make a black body spectrum in the lab as perfect as what was found by the COBE satellite in the late 90s of the actual black body spectrum of the CMB. And of course, then from that spectrum, we can calculate the temperature using Planck's spectrum distribution law. So we predict the actual black body spectrum at the right temperature and with its temperature and asotropy characteristics. As we look in different places at the CMB, we will find slightly different temperatures. They are not, in fact, homogeneous or isotropic. They have an anisotropy. For the CMB, the calculation of the density variation of normal matter on the largest scale. From this CMB, we can go ahead and extract what the density variations that we see, and in agreement with our observations like, for example, the Sloan Digital Sky Survey. The calculation of the polarization of the CMB and its agreement with the current data. For example, the degree angular scale interferometer down in Antarctica. So there's a tremendous amount of evidence that supports, do I have one more? I do. Using initial conditions consistent with the CMB, creating the supercomputer simulations, which we've all seen, we actually can do the evolution and distribution of the large-scale filament structures of the universe, of the galactic global structures. So it's a imposing theory. It has tremendous evidence, it has tremendous support. So when we come to that last slide and we ask about, well, what's wrong with this thing? Let's change it in some way. Okay, you can change it, but you got to keep these things right. You can't move away from these things. So you'll be working with one hand tied behind your back as a theorist. Okay, so let's get to the actual process of using the CMB for the calculation of Hubble's constant. We'll take the latest data, the Planck Anisotropy Probe of 2013. I remind you of the COBE and the WMAP, the late 90s, the mid 2000s up to 2010, and then finally the Planck probe, which I think the last big broad data dump was done 2013, 2014. I think it's fair to say that this is the most analyzed phenomenon in the history of science. If anybody knows of a phenomenon that has been more analyzed and more information gathered from it than the CMB, I would really like to know, because the information that has been extracted by analyzing these speckles of differences in temperature is really just remarkable. You can see here we have the blue and the red and anisotropy points. The average temperature is virtually, if you're working to 3 decimal places, this is a completely smooth map. This is one temperature. You have to go down to the 4th decimal place, 1 part in 100,000, given the fact we start with a whole number. And that you have to go down to the 4th decimal place before you see the variations in temperature as you move across the sky. And think about what it takes, guys, to make this map, right? You have to point your telescope in a spot, take the spectrum of the CMB, take the entire spectrum, the whole graph, I have a black body spectrum. Run it through, first of all, run it through all the filters to clean it. The instruments that you need have to be super cold. So we're just seeing this very, very faint message. Run it through your Planck energy distribution, black body distribution curve to get the temperature, to get the average temperature. And then do that again with another spot, another spot. Every spot here represents that analysis of looking at the entire black body spectrum coming from that spot and calculating from the spectrum what the average temperature would be. And they vary by very, very slight amounts. And these slight amounts in this pattern of parts hotter and colder above the average is what this famous picture that Rick Bates has so wonderfully behind him comes from. Okay, so maybe for our purposes, besides the Hubble constant being measured from this pattern, maybe the other most important thing among the many that have been derived from the analysis is the actual geometry of the universe. Whether we have an open, closed, curved, positive curved, negative curved, or a flat universe. And what the CMB has convincingly shown is that our universe on a whole is flat. Not that parts of the universe are not curved, not that general relativity is wrong, not that there is great curvature around the sun, which causes the light, of the eclipse of 1919 to bend. No, not that curvature. The curvature of the universe as a whole. That's what we're always talking about in cosmology. And one can actually calculate what these distributions should be, what kind of average sizes these distributions should be given the different geometries. And surprise, the one that wins, the one that, the predicted one that we see is the so-called flat geometry. The one where great triangles in the universe would be 180 degrees, as they should be in any self-respecting Euclidean space. This will become important for us and later on to realize that what we are dealing with is a flat universe. And therefore, that I mentioned before about the energy density of the universe, the overall energy density of the universe, given the fact that our universe geometry is flat, general relativity tells us that therefore the true energy density of the universe must be the critical energy density calculated from general relativity. That will play a role for us as we get to the accelerating expansion of the universe. Okay, that's the first thing that the CMB will do. Let me just mention one place in the whole 13.8 billion years, the era of recombination. That is when the great plasma ball, expanding ball coming from after inflation, finally cools down to 3,000 degrees, when finally the hydrogen and helium nuclei, deuterium nuclei, can finally capture the free electrons and be left unmolested by the photons. The photons will have been cool enough, the whole environment is cool enough that those photons cannot immediately reionize the atoms, and the atoms become stable. What that does is it allows finally for the light to be released. Until that point, the photons were always heading into free electrons, always being absorbed and then readmitted by electrons being changed their energy values all the time, and they never get anywhere. And so what you have is literally just a cloud in which, the light can't actually move, can't actually get in any particular direction. It's constantly being scattered. At recombination, that finally stops. Finally, the light is the radiation part of the energy density of the universe at this point, calculated to be 3,800 years after inflation. Finally, when that happens, that is the light that is released. That is the cosmic microwave background. Okay? And that is what has been moving through the universe ever since, getting cooler and cooler and longer, and the wavelengths getting longer and longer until what we see now is approximately 3 degrees average temperature, from that initial 3000 degrees when it finally was released from this plasma. Okay, so it is this place that we want to focus on, because what this is going to do is the light, therefore the cosmic microwave background has frozen in it, implanted in it, the characteristics of the matter plasma at that quote moment. Okay, whatever's been going on in the plasma of protons and neutrons and nuclei of such, mostly being hydrogen and helium, whatever's been, and forgive me, and the dark matter, plenty of dark matter here. The signature of where the dark matter, I'm sorry, where the matter is, how it's distributed, how its density is distributed, is imprinted in the cosmic microwave background as it's being released. That's what's key to understand, that it's being released in a way that is reflective. The temperature that's being released of the light energy is reflective of the density patterns of the matter that's finally coalescing into normal dark matter and normal unionized regular matter. That is the key idea to take forward as we look at what you can do with this to find the expansion of the universe. And it's all in here in the terrible name, the Baryonic acoustic oscillations. Baryonic, of course, a fancy name for us for just protons and neutrons. What's going on here is this plasma, for all the 380,000 years, has actually been subject to sound waves. Literally, it's a fluid. It's a plasma fluid, not a plasma that we think of. It's a plasma that's beyond, temperatures beyond anything that we can create in the lab, but it is modeled as a fluid. And so there are waves, push-pull waves going on in that fluid as it expands. And when recombination comes, and what's causing these waves is the push-pull. Gravity, the dense parts of the plasma are trying to make itself more dense by pulling it together. The radiation pressure is pushing out, and so you're literally getting a push-pull, and that's where these waves are coming from. Once the radiation is released, the push-pull stops. We only then have the pull, right, of gravity, both on regular matter and dark matter. We know the light energy never affected the dark matter, never did. The light energy was only with the push-pull of the regular matter. But when that stops, we will get, according to theory, an imprint on the radiations being released of what that density looked like as the light left it behind. And that's what this is representing. And what I really just want to talk about is this very extreme peak. What's going on here? These are just simply, the x-axis are angular separations. What do I mean by 1%? I simply take like a compass, two ends of a compass, and I hold it up to the cosmic microwave background with a separation of 1 degree in the sky. And I go ahead and I take those 2 points, get their temperature, and just see what the difference in temperature is. Is it a great difference in temperature, that 1 degree separation? Is it a very small difference? I simply make an accumulation of what the different temperature differences are, all the different sample points that I take that are all one apart. And what I find is at that one separation, I get a very, very large amount of large energy, very, very large temperature variations. The temperature variation at 1 degree is on average much larger than any other any other angular separation. We have another one here around a ½ degree, another one here as we go down. These are all quite predictable given the state of the plasma and the temperatures that are involved and the particle physics and the acoustical science and the Fourier analysis and all of that's involved, that these are quite predictable. And it's quite amazing that this graph is beautifully predicted in theory by the model. What this then tells us is what is the predominant separation of the dense parts of the plasma as it finally became regular matter. Those dense parts will, in a sense, stay as the universe expands, they will not just simply dissipate. They are there, gravity has them there, and gravity will hold them there. And the dark matter, which will halo around it, will in fact help reinforce and keep them there. What we'll wind up with is some kind of a primordial ring size that will grow and can be, and predictably grow from the sizes of this graph. This is where the cosmic microwave background looked like at the time of recombination, this kind of size. So it's quite an involved analysis. It's the best I can do with the time that I have. The point is that those primordial rings have to grow in size as the universe expands. And these rings are recognizable. And as we look further back in time and closer in time, as we see these rings expand, we can measure the expansion of the universe. And one of the things that comes out of it is the current Hubble constant. Okay? And a Sloan digital survey, probably the greatest ever done, final data release given out just last year, shows these ring structures, these density structures within the great galaxy clusters that are being stolen. It is quite remarkable that this is done. The ability to predict something on such a large scale from such a scale so far back, 380,000 years after the Big Bang. So this is quite remarkable. Again, you don't trifle with this theory easily. Okay, let me stop here because I'm about to go into we'll go to the other side of the street of looking at the more conventional idea of, we think of Hubble's law of looking at redshifts in distance. Eric, do we have any questions so far?
No questions currently in chat, a couple of comments. If anybody would like to unmute themselves and ask a question or type something in chat, we will take it. Going once?
Peter, I'll speak up here on one semi-question, semi-statement. On
Claudio,
the various,
Claudio, is that you?
I think so.
I recognize your voice. Hi, Claudio.
Yeah, hi. Well, on my screen, I'm two screens over from you. There has been some discussion that so I'll put it in the question form is what I'm saying, that the various methods of measure, which are dependent on separate phenomenon, celestial phenomenon, are affected by the intergalactic medium and interstellar medium impact on the photons that are en route from those celestial targets, and that the effect is different for different kinds of phenomenon, and that may be, it's hypothetical, it's speculative, may be a factor in the perception by our instrumentation of the various variations in the Hubble constant. Have you heard any of that kind of debate?
Yes, I have. But as you well know, Claudio, you put 3 theorists in a room and you'll get 4 different theories. So
exactly, every time. Yeah.
Yeah, every time. Actually, 5 probably. So yes, that has been put forth among many other things. And Claudio, you have preempted my next to last.
Sorry. All right.
No, it's dealing with a crowd like this. I just come to expect it. That's all.
All right. Good job. Keep going. I'm done.
Okay. All right. Eric, should I go on?
I see no other questions, so I think you're good.
Okay, so let's take a look at the measuring of the Hubble constant in what we would conceive of as a more conventional way of the Hubble constant is about speed and distance, proxy, redshift to distance. So what about measuring those things and seeing what we get as a divisor? I'm sorry, as a ratio. It's an interesting graph going back to the very beginning. You may know from your history that Hubble's first estimate was 200. As you know, Walter Bade went ahead and found during the war, when he had the Wilson telescope all to himself, being a German national stuck in Mount Wilson all by himself, went ahead and went through and recalibrated all of the Seifert variables that Hubble was using, and found that he was off by a half, and that Bade in one stroke went ahead and doubled the size of the universe. A fascinating story. So the Hubble constant has been coming down and bouncing around. And the first real kind of modern measurement, very interesting, was done by Hubble's protege, a student, PhD student of Bade, and one who worked very closely with Hubble, in his career. Basically picked up his research project after Hubble died, Alan Sandage. And Sandage made the first measurement in 1958 of something which approached, 75. Well, it's interesting if we think the answer is around 70. This is not bad. Way back in, things haven't really changed all that dramatically. What's all the hubbub about? My goodness, we can't. So it is kind of funny that he really hit upon a very decent number very early on, using the fundamental program of the Seifert variables, which I'll mention in a bit of detail in a moment. The other historic one that you really want to give credit to is Wendy Friedman's and her team in Chicago's measurement considered the beginning of the opening of the modern era of measuring Hubble's constant of 72 plus or minus 8, a wide band, but still that 72 being considered a very good number at the time. And she, of course, is the queen, at the time at least, she was the queen of Seifert variables, making painstaking calibration measurements. And so her number was taken very, very seriously at the time. And she is still a major player, as we'll see, in this space of measuring Hubble's constant. Okay. Before we go on to distance, the cliche is redshifts are easy. It's the distance measurements which are hard. And this is, of course, true. But give me a moment and let me just take a look at redshift with you. Again, the redshift, traditionally the letter Z is used, is the change in the wavelength from measured to what's considered the lab measurement, the one that you would measure from rest, divided by that rest wavelength. And if we just do a little bit of algebra, we can go ahead and divide, lambda 0 into top and bottom, and we'll get Z is equal to lambda m over lambda 0 minus 1. We can bring the 1 to the other side and get this very interesting number, Z plus 1. Z plus 1 is the ratio of the measured wavelength, the elongated redshifted wavelength, compared to the so-called source, stable source, stationary source wavelength. We can do one more thing. We can turn both those upside down and get 1 over Z plus 1 is equal to now putting the stable source on top. This number, 1 over Z plus 1, lambda 0 over lambda m, is called the scale factor. An important concept, again, in the whole Friedman equation analysis that you'll study when you go ahead and look at some of the general relativity behind this model. One more algebraic manipulation, if I may. Solving for lambda 0. Lambda 0 is equal to the elongated wavelength, here going from the initial source to the elongated one as the universe is expanding, is equal to the measured over Z plus 1, the scale factor. And so we can say in words that the original wavelength that was released, at that time, whenever the source released it, that we're looking at, has been scaled down by a factor of 1 plus Z plus 1. Alternatively, one can say that the fabric of space-time, during the time that this light has been traveling from this place of Z plus 1 that has a redshift of Z, has been stretched by a factor of Z plus 1 as lambda m has been stretched. An example. If Z is equal to 2, for example, then 1 over Z plus 1 is a third. And one can say that therefore the size of the universe, and I should say the observable universe, the size of the observable universe at Z plus Z is equal to 2, when this object that we're looking at that has a z of 2, when the size of the universe, when the light was released that we're looking at now, analyzing this redshift, was about the third of the size of the universe today. A nice kind of, I think, is a cool kind of calculation. Summarizing in general, for a source of redshift z, the size of the observable universe at the time that the light left the source was about 1 over z plus 1 smaller than today. Well, let's take maybe the most interesting one. Let's take the redshift of the CMB itself. Turns out, because we go from 3,000 degrees down to 3 degrees, that the redshift calculated to be about 1100. So 1 over z plus 1 is about 1 over 1100. And therefore, we can say that at the time of recombination, the observable universe, our neck of the woods that we can see, was about 1,100 times smaller than it is now. It's a remarkable thing to be able to say. I think kind of blows me away that we can make such incredible conclusions from such simple ideas, working inside, I hasten to say, a very powerful theory. Okay, I promised you that we could straighten out this simple formula that we have, that the velocity is simply a fraction of the speed of light when z can get bigger than 1. This first graph here is the one that I first introduced. This basically is a Doppler formula that would work for sound just as well, up to reasonable z's of maybe a half. Clearly, this is not going to work. If we use the Doppler formula for special relativity, that's not going to work either, because we know that relativity will never let us get above the speed of c. Okay? Turns out that general relativity will allow you to do that. Okay, and the question that is often asked is, but isn't that a violation of special relativity? And the answer is that what special relativity says is nothing can move through space at the speed of light, except for photons, things which have no mass. General relativity does not put any, special relativity doesn't put any restrictions on how fast space can actually stretch, how space can actually expand. And so that's what the redshift is actually measuring. It's measuring the expansion of space, not anybody moving through space, but literally the space between us and them, the redshift object that we're measuring, the space between us is actually moving apart. And so this is why we can just use, for simplicity, in our graphs, just redshift versus distance, because the redshift that we're using is the one dictated by the theory of general relativity. And you can see for z's up to about 1, they really do coincide. So you're working with small values up to like 1 billion light years, for example, something in that neighborhood. You really are working with a very simple formula. Okay, so what we're going to be working with is the famous cosmic distance ladder. Okay? We begin with simply bouncing radio signals off of the moon and off of Venus, etc., to getting measurements within meters. And then we go to parallax. Okay, the first really great measure that gets us beyond ourselves. And the biggest development there is Gaia. Gaia has been out there for 6 years in orbit about 1 million miles above the Earth, and it just released its next great dump of data. I think 1.3 billion stars have been measured through its parallax, given its incredibly large baseline and its incredible optics, and not having anything to worry about in terms of the glare of the sun or the atmosphere itself. And people who should know, the builders of the Gaia, say that this is about as good as it's going to get. This is about the best parallax measurements we're going to get for the foreseeable future, given the technology that we can conceive of. So this has been a great boon to this whole enterprise, because clearly every rung in the ladder supports the rung above it. Well, the rungs above it don't have much to stand on without the rungs below it. And this parallax rung is so important, because it's the parallax measurements of the Cepheid variables. The Cepheid variables that we can measure with parallax allows us to calibrate the measurements, the distances of the Cepheid variables that are beyond parallax, where we have to go to Leavitt's law and look at their period. This was covered very nicely in Claudio's talk last month, so I won't belabor this. He told the story of Leavitt Swan, Henrietta Leavitt Swan, and where the standard candle law comes from, but you can see it in summary here, that you can measure the inherent luminosity of a Cepheid variable just by measuring its period. And so by properly calibrating those Cepheid variables, which we can measure independently by parallax, we can then go ahead and get the inherent luminosity of ones that we can't by just measuring periods. Once we have that, we go to the next and most important and maybe really last kind of, I don't know, physical law phenomenon kind of standard candle, and that's the type 1a supernova coming from the white dwarfs. And I'll mention this just in a moment. But the idea is the same. It's a standard candle because we have some way of measuring the inherent luminosity of this thing by measuring something else other than redshift. We don't need to rely upon Hubble's law. We have another way, like Cepheids, we can measure the period, and for type 1a supernova, we can measure something else that will give us the inherent luminosity. Again, we have a calibration going on. We take those supernova that we can measure through Leavitt's law, through Cepheid variables that share the same galaxy, and measure our luminosity law, whatever that is that we're trying to calibrate, against our Cepheid variables, which depend upon the ones that were measured in parallax. And then we go forward measuring supernova way beyond anything that has any kind of Cepheid variable that will be visible in it, but we rely upon the calibration of that new phenomenon. And the last desperate hope is, after you run out of that, you can simply just use Hubble's law. You can just simply take the redshift and divide by the best Hubble constant you have, and that will tell you the distance. Okay, so let us just take a moment and look at that all-important standard candle of the type 1a supernova. Okay, the life cycle of a star, going, coalescing, becoming a star, developing into a red giant, expanding into a planetary nebula, and then finally shrinking into a white dwarf. This is material more familiar to some of you than to me, I'm sure. If you've taken any of Claudio's astronomy courses, you know much more about this than I do. This basically is the sequence that our sun will follow. White dwarfs don't inherently become type 1a supernova. Something has to happen. And as unlikely as it might be, two white dwarfs can begin to merge together, becoming more and more massive by hitting a certain mass, 1.4 solar masses, or more likely a white dwarf with its tremendous density, its tremendous gravitational pull, can pull upon a nearby star, maybe conveniently becoming a red dwarf. So it has a very tenuous atmosphere, and it can be sucked in, and that white dwarf will grow and grow in mass until it hits that Cassandra limit of 1.4 solar masses, and it will literally annihilate itself. It will blow up without virtually any remnant, and that is one of the great fireworks of the universe. It can be 5 billion times more brilliant than the sun. These can be seen at great distances. Are they a standard candle? Yes, and not surprisingly, where you find that phenomenon is in the light curve. If you go ahead and measure from the peak brightness and watch it dim as the time goes on, as days go on, some of these supernova will dim slowly, and some of these light curve will dim very, very quickly. And by looking at these supernova that we can measure their true luminosity as we watch the observable luminosity, the apparent luminosity dim, knowing the brightnesses that we have from Cepheid variables, we can go ahead and calibrate these kinds of light curves. So that when we see a supernova way, way out, way beyond anything we could see of a Cepheid, we watch the light curve and see its rate of decline the luminosity declination rate relationship, and from it we can deduce its true luminosity. And as with all standard candle operations, you have two fundamental numbers. You have the inherent brightness, and you always have the apparent brightness. That's, of course, if you're not worrying too much about dust, or you can accommodate the dust. We well know there's nothing simple in astronomy, but if you can get the inherent luminosity and the apparent luminosity, the simple laws of light will give us the distance of that object, the inherent idea of a standard candle. Okay. This all leads to the great discovery by the two teams working in their data published virtually simultaneously in 1998, which leads to the accelerating expansion of the universe. The leaders of the teams won the 2011 Nobel Prize for this work. And here's what we're looking at, guys. We're looking at their data. This is actually their data. I remind you of Hubble's law, and notice that we have redshift in the x-axis and distance in the y-axis. And so we actually have the reverse of Hubble's law. We have distances equal to redshift down below. And so we're looking at actually 1 over h sub 0. Okay, so this is what Hubble's law gives us. And notice that the data of very, very close is very good. This team found that the current version of h sub 0 was very good, tremendous linear relationship. As they looked further and further out, using their calibration, looking at further and further supernova, out to z's of I think around 8 or 9 is what they ultimately got out. This data here is out to redshifts of 1.6, but I think some of their data got out. Maybe not. Maybe that's I'm thinking of quasars. Their data went out way beyond z of 1 anyway. Their data began to drift. Their measured points, their measured data points with their error bars began to drift off of Hubble's law. Hubble's law clearly was not being followed the further we went out. So let's just see why. Let's take a typical point. Okay, here we have a typical data point. Right? This is a measured point. Right? This is a measured redshift. That's the easy measurement, right? And we take the a redshift, a wavelength that we recognize in the spectrum, and maybe a part of the spectrum of hydrogen. In the fact that it's 3/4 of the universe, good bet that it could be a hydrogen spectral line. We recognize that it is such, and we see its redshift. Redshifts are relatively straightforward to measure, as whatever gets to be straightforward in astronomy. Using the light curve of the type 1a supernova, we can measure the distance. This is a measured point. But if we go to what Hubble's law would dictate, and we get the expected redshift, we find the expected redshift is much greater than the measured redshift. And this is consistent. And the further we go out, it seems the worse it gets. This is their data for both teams. How to explain this? Why is the measured redshift less than the expected one? The answer, well, the stretching of space-time, that is the expansion of the universe, I guess was not as great back in the past as it is now, because we're not getting that kind of distance. We're just not getting. The distance we're getting is not what we would expect from the expansion rate that we would be using the Hubble constant. What we find is that the universe was not expanding so quickly in the past, or the universe's expansion is now accelerating. And that, of course, is the great discovery that really changed the game for everyone. And what it did was people went back to the drawing board of the equations of general relativity, and we had to introduce the concept of dark energy. And with it, the original sin of general relativity in terms of Einstein's work is to bring back a non-zero cosmological constant, which is essentially the mathematical equivalence of having this concept of this negative gravitational energy, this negative pressure pushing against space, which is causing this accelerating expansion. Okay, so we're about to now finish the talk. We're going to go into the players. Here are the current players of measuring H sub 0. And let me just stop one more time before I run through these characters. It's kind of a fun thing of what they're doing now, the different kinds of measurements they're making. But Eric, I'll stop here one more time if there are any questions.
I see none in chat. So again, if you'd like to ask a question, feel free to unmute yourself or type something. Going once. Going twice. Okay. To you whenever you're ready, Peter.
Okay, thank you. Okay, let's start with one of the people on one of the teams, one of the leaders of the team, Adam Rees, who geared up a new project called SHOWS, which is dedicated to measuring the Hubble constant. He is an expert, became an expert, of course, with his work on the type 1 A supernova as benchmarks, as measuring the acceleration expansion. He has become an expert on the Seifert variable calibrations. He, in fact, just published just a couple of months ago using the new Gaia data, new calibrations of Seifert variables, which of course is a key rung on his ladder so that he can move on to the supernova calibrations to get his measurements to get a good measure of H sub 0. His latest number is 73.2 kilometers per second per megaparsec, with a margin of error of 1.8%. He is very confident. This, by the way, is a picture in the summer of 2019. You can see, if you can make it out, there are the bars, there are the different measurements of the different teams, and the Hubble constant tension, well, maybe it's a problem. And at the end of this talk, the story goes, he declared it a crisis. When the difference in the error bars got to be greater than 4 sigma, which 4 sigma, 5 sigma is the usual typical thing we learn in school, that once you got that far out, the probability of this being wrong by chance is very low, measured at 1 in thousands, hundreds of thousands. So that's the graph that's in front of him there. The next group is I have a senior moment. Wendy Friedman is back in the game, and she is very interesting using red giant branch-tipped stars. You can recognize the HR diagram here. We have the main sequence. We have our sun will eventually head in this direction, going up through the red branch. And finally, when it really blows up, here we are at 100 solar radii, when the helium core ignites. It ignites as a flame burst, as a short-lived, incredible flame burst. And at that point, it gives off a characteristic peak brightness, one that is repeated in this branch. That is, virtually all stars starting from that point in the main sequence going up through that branch will have the same inherent luminosity at that point of the helium burst, right? The very definition of a standard candle. So by calibrating, again, she is the original expert on Seifert variables. By calibrating these measurements here, these distances against the brightness of the helium burst against known distances of the Seifert variables, she has a brand new standard candle to use, which she feels is more reliable than her wonderful Seifert variables that she relied upon for all those years. She feels that there's less chance of error. Seifert variables do change in kind of a radical way over time, where the periods may be subject to some kind of change in terms of the Leavitt's law thing. This helium burst is very short-lived. She feels it's more consistent. The red giants are they're older stars. They're out in a cleaner part of the galaxy where perhaps there's a chance of less dust, which can be a big problem. She has her reasons why she's moved to this direction. Okay, but what she has found is 69.8. Her error bars are getting better. They're not quite as good as Reese's, but she's getting better. She's a highly respected person in this field, and she is really not budging an inch. And she and Reese really are pretty much at loggerheads. We've got Holy Cow. Holy Cow uses a totally different idea, and that is of gravitational lensing using quasars. It's very, very interesting. We know the concept of a galaxy that gets in front of an active galaxy which has a quasar, and not through so much through its mass, but the mass of the dark matter halo around it. That tremendous amount of mass can cause the bending of the light and create multiple images. Well, quasars change. Quasars fluctuate in their brightness, and it turns out if these trips are of significantly different distances, which they turn out to be, the images coming from one path will change, will flicker before we see the change coming from the other images. Makes sense. And we can measure the time difference between that change in brightness. That will tell us what the different distances there are. They do use the redshift of both the galaxy here in front and the quasar, but it's a complex calculation which I don't fully understand. But the actual change in distance of these trips is what they use directly, in a sense, to get, well, how has the universe space been stretching? Because this is coming from very, very far away, these quasars, right? This is nothing like what Reese and Friedman are using. Okay, they're working in the area of maybe 2 billion light years. We're talking now very, very high redshifts. We're talking, 6, 7 billion light years. So we're talking about a tremendously long trip that's being made, very much what Claudio was talking about. Because the trip is so long, the time delay, the time difference can be used to get after the actual rate of stretching itself and come up with the value for the Hubble constant. And they have a number very close to Reese's. He's delighted with that. They have a similar error bar, and these guys are in cahoots. The Holy Cow folks and Reese's shows people are very much on the same page and feel that they've got a very good story to tell, because these two methodologies are quite different, although they agree quite well. And the last one I want to mention here is a brand new one, which is using gravitational waves, right? We go back to 2016 when they were first detected in the LIGO interferometers, right? One in Washington and one in Louisiana, where a black hole was causing the gravitational waves. Here in 2019, 2 neutron stars collapsed together and created tremendous gravitational waves, which were detected. But the great thing about the neutron star collapsion, the 2 neutron stars will give off both light and gravitational waves. Well, the light can be measured for the redshift, and the amplitude of the gravitational wave will give us the distance. Not 1 over distance squared, interestingly, but according to general relativity, it's 1 over the distance. So by measuring the characteristics, the signature of the merger, we're getting what the amplitude should be at the time of the waves were created. Measuring the amplitude now, we can get the distance. They very much, the Holy Cow people, again, are very excited by this. They've only got 1 data point, so the error bars are very big. But they feel this is a completely new way of doing it, having nothing to do with distance and using the cosmic ladder. It's totally free of the cosmic ladder. It's its own cosmic ladder all by itself using general relativity, and they're very excited. This group is very. I'm sorry, did I say Holy Cow people? Those are the quasar lensing folks. These people here, the LIGO people, are very excited about this, and of course using a brand new phenomenon. I believe LIGO was shut down now. It was shut down originally for the pandemic, but it's now being recalibrated even, I don't know, it's just beyond the imagination. Instead of being able to distinguish between two proton diameters across change in distance, they're going to do one diameter. You know, it's beyond limit what the sensitivity of this can do. And there are other LIGOs, right, coming online in other places. But their number is also very interestingly close to Wendy Friedman's number. So there's a whole free-for-all going on here. So now what? Here we have the summary here. The red bars, this is the cosmic microwave background. This is the latest data coming from Planck. And here is the consensus right now of people like Reese and Holy Cow coming in at around 73 or so. And here's our gravitational waves, right in the middle, and also right in the middle, someplace here, I guess here, this would be Wendy Friedman. So we've got quite a conundrum. What is to be done about this? My last slide, which was preempted here by I think it was Rick. Okay, so what are the things that can be done? Well, one possibility is that the distances that we're measuring are wrong. We all agree that they are tough. They all depend upon the calibration as the ladder goes up. However, big but, the Gaia parallax measurements of the Cepheids, they're about as good as they're going to get. This is the best you've got here. And they really are very, very good. So you gotta be pretty confident of your cosmic distance, at least on the first rung. And the Cepheid stuff has been around a long time, and that's pretty confident and been corroborated going back to Wendy Friedman's work. So you know, they're not budging much on this one. You can continue to research and calibrate the supernova stuff. You can look hopefully for more gravitational wave data points. They're hopeful for that. And you can look for other standard candles, which there are, which I really had no time to look at. But there are other standard candles that are being used. Second possibility is that there's something wrong with the cosmic microwave background data. Not the data itself, because the people who know say that Planck data, that's about as good as it's going to get for a while. That according to the foreseeable future, that is about the best design of the most accurate anisotropy measurements that you're going to find. You know, when you read the literature and you read the what was happening at the time, you know, the people who were looking at COVID say, well, you know, the WMAP stuff will be coming online, and that certainly will, you know. And then when the WMAP information was out, well, the Planck stuff is about to be launched in a couple of years, and that certainly will. And certainly the data did get much better, and the error bars did shrink, but it's not like they said the same thing. I just even last year or so, I read, well, when the Gaia information comes online, that will certainly resolve the problem between. It doesn't seem to work that way so easily. People stick to their guns because of the methodologies that they use the data, but they've got their reasons why they analyze it differently. The third is, well, there is a fundamental problem, maybe with the model itself, as powerful as it is. What do you got to look at? Well, you got to look at what underlies it. General relativity, dark energy. One of the big things that are being looked at is maybe the dark energy, which is assumed in the model, is constant. It is, after all, the cosmological constant. That's what it's doing, sitting in the equation. Maybe it's not constant. That would go a long way in solving this problem. Dark matter, also an unknown, which is the bulk of the matter energy density component of the model, and maybe the computational methods there are not correct. God knows we don't even know what the gosh darn thing is yet. And in looking at the quantum stuff, the standard particle physics, again, you have to be looking at dark matter. Still don't know what it is. Still don't know what its possible interactions could be. Again, I go back to Claudio's observation that maybe as these photons are going through, maybe they interact in some way with light after all that we're not getting. We're missing something. And you know, and finally, the last one that was promised at the very beginning of the talk was new physics, the most exciting possibility of all, right? That we're missing something fundamental A good guess is if there is something fundamental, there's something fundamental about the processes of the early universe and the late universe. We're missing something that's either happened that doesn't happen anymore, or vice versa. But it's got to be deep and fundamental to shake up the underlying theories that we are using and the confidence of the data that we're analyzing. So that's where things stand, guys. And that is what I have to say. Thank you for your attention. Eric?
So now we're in the Q&A portion of the talk, so kind of a free-for-all at this point. Feel free to unmute yourselves and have at it. Discussion's also welcome. If you prefer, feel free to type questions and comments in chat, and I'd be happy to read them out for those who don't have the ability to read that.
Yeah, Peter, I'll chime in a second here again. Do you know who is pursuing pointedly these questions about super distances back in time as well as physical distances and the influence of dark matter on baryonic matter and baryonic photons, if you will, passing in our direction? Do you know if there are any conscious efforts at that research, any teams working on that?
Claudio, I don't. As you can imagine, the research I've done here is focused on the experimenters and not the theoreticians. So I don't know much about the theoretical work that's going on in the background. I know there's plenty, but I have in my notes here in front of me, I can tell you about the people who have been doing all these different measurement methodologies and analysis, but I really don't have much of a handle on the theoreticians.
Very good talk, by the way. I thank you for this. This kind of stuff can really get creepy, and that's what makes it so wonderful. Because our day-to-day lives, we take for granted that we know how things around us work, and then something like this comes up, and you realize that the carpet may be able to be pulled out from under us.
Well, in that regard, Claudio, if I could just amplify that, there's the famous picture here, right? That what we thought, I don't know, 15, 20 years ago was the entire universe, the entire subject of science, going back to the beginning, 10,000 years of civilization. What we thought was all of it is now we realize is 5% of what makes up the universe. And another consequence of the model, the analysis essentially of the cosmic microwave background and its aftermath. So I think just underlying the point that Claudio was making.
Rick Hunter is asking, well, first he's complimenting your talk, and then he's asking if you would be willing to share your slides.
Yes, what I'll do, Eric, is if I could I email it to you? That be okay? Have I lost you?
Sorry, I lost your audio there for a second. Could you
Okay, I
repeat
think
that?
I'm back. I got that terrible message, unstable connection, but it's gone. Eric, could I email that message to you? I'm sorry, email the PowerPoint presentation to you?
Eric, he's asking if
And then you could distribute it to folks.
Oh, yeah, that'd be fine.
Okay, great, thank
I'd
you.
like a copy for sure as well, Eric.
Okay, I know I have Margot's email address. If I could send it to her, or if you want to send me a message.
Actually, on the board
resend it
meeting next week, it is something we can
to
probably put
you.
out on the one of our mailing lists or even up on our website. But yeah, we'll make that available if that's okay with you, Peter.
Your email list is on the website? Fine. I'll pick it up there. Well, if there's nothing else, then I'll stop the recording. There are no other questions? Have I lost everybody?
It's coming in and out.